Hello again. So I'm going to look at a claim that's made in several Flat Earth videos concerning the view of the sun in the Arctic Circle during summer solstice time, when you can see the sun for 24 hours. There are a couple of claims around this, and I'm going to play a minute or so of this video by Rory Cooper. Interestingly, his channel is now missing from YouTube. This was first published about 18 months ago. I don't know. Maybe he realised the error of his ways and he's disappeared. But in any case, this myth or this argument still carries on. I've seen it in several more recent videos, and I'd like to talk about it and just explain what's actually going on in reality in the heliocentric model. So let me play this and then we'll talk about it.
And you look at the video footage, it becomes clear that we are living on a flat plane and the sun is actually orbiting us. So the one issue was that was brought up against the zigzag theory is the distance of the sun from the cameraman. But that's not the issue. So the point is the cameraman, he is moving. And it's his video footage of the sun. He is moving from left to right. So therefore, the sun would have to zigzag. In other words, I've got a man here, I put numbers around him. Right, you see, the numbers would turn, but he's facing the beer. He's not turning 360. All he's simply doing is he's turning to his right. Now he's pointing back forward, and now he's pointing to his left. He's not rotating 360, because if he did rotate 360, the beer would be behind him. You can't see the beer all the time. And did you notice? Look at that again. Now look at that and look at the numbers. You see, as he rotates, the numbers rotate with him. So as he looks at the sun, you see 1, 2, 3, they're all passing. Right? And now 1 passes, 4 passes in. Now 1 passes in again. But if he rotated, you see, he'd be looking at the same number in front of him, and the beer would be behind him.
Okay, so that kind of puts it in a nutshell. There's two main claims being made there. One, that because of your left to right motion as you're rotating around the Earth, or the Earth is rotating, that the sun would appear to zigzag in front of you, and so you'd have to point left when you're on the right side of the Earth, or right when you're on the left side of the Earth, to keep the sun in view, so that as you're looking at the sun, it's gonna, if you're trying to fix yourself and lock onto the sun, you're not going to continue in a steady 360 degree circle. At points you're going to zigzag back and two. The other claim made is that he's not really rotating, that he's not rotating 360 degrees because he's fixed his view on the sun, and as the Earth rotates, because he's fixed on the sun, he's only really seeing 180 degrees, because if he turned his back, then the sun would be behind him at any of those points, and he's always facing the same direction, hence he's only seeing 180 degrees. So I'm going to address those two claims and those two issues and show the flaws in these models. But first of all, we need to calculate the viewing angle of the sun, or talk about the viewing angle of the sun. So as I said, the problem here in these videos is one of scale. Always you'll see the Earth represented like this, a big ball, and the sun as a small, close point. So once again, as our guy is on this side, he'd look right, and on this side he'd look left. This is looking down on the Earth, North Pole up here. So what we need to do is to find a way of working out what the angular change is between the left and the right sides of the Earth. If you're on this side versus this side, what is the angle difference that you would see? In other words, how much would that sun move backwards and forwards in the sky? So let's find a way of doing that. And I'm going to take you through an example first of all. And there's our little guys, by the way. He's on this side of the Earth, and now he has to rotate to his right to look at the sun. And he's on the right side of the Earth, and now he's had to rotate to his left to look at the sun. Now there's a pretty easy way of finding out what this angle is. We can draw a triangle. So I've drawn this out as an equilateral triangle, so that we can do the maths, check that it works, now because we know the angles, and then we can actually put the figures for the distance from the Earth to the sun in and see how that works out. So because this is an equilateral triangle, all three sides are the same, all three angles are the same. Angles of a triangle always add up to 180 degrees, so we know that these angles are each 60 degrees, 60, 60, 60. So this is a 60-degree angle. We know that before we start, but we're going to do the maths to work it out just as a proof of concept. So here's our angle. We know that's 60 degrees. But this is the angle we're going to find out, so let's pretend we don't know that's 60 degrees. What we're going to do is split this triangle in two and create two right-angled triangles. There's one, and there's the other. But we're just going to concentrate on one triangle, because if we can work out this angle, we're going to call it A. Then we can double it and find out the total angle. Pretty simple. So I'll put some numbers in. Now the Earth is almost 8,000 miles wide, so we're going to use 8,000 because it's 7,900 or so miles wide, so it's close enough. Makes the numbers easier. So if this distance here is 8,000 miles, then half of that here is 4,000 miles, so we know this side of the triangle is 4,000 miles. There's a formula to calculate the height of an equilateral triangle, which is half of one side, 4,000, multiplied by the square root of 3. You can try that yourself and measure it. It works. It's a formula that works. So that gives the this side of the triangle a distance of 6,928.2. So now we have this side and we have this side. So we're going to work out this angle A. And we do that by using the law of tangent. If you remember back to your high school maths, the tangent of an angle in a right angled triangle is equal to the opposite, 4,000, over the adjacent. So what we're going to do is we're going to plug those numbers into to save doing the maths. We have a calculator here. Great online calculator, Carbide Depot. So we can plug in any of these attributes and find out any of the others. So, side A, that was our 4,000. Side B, that was our 6,928.2. And now we can hit calculate. And that works out that angle A is 30 degrees. This was rounded in the first place, so that's why it's not an exact figure, but it's 30 degrees to several significant figures. So let's go back here. So now we know that A equals 30 degrees. So fairly obviously, 2 times A is 60 degrees. So we've just worked out from this distance and this distance that this angle is 60 degrees. That's our proof of concept. We knew that before we started. So now we can actually plug in the figures for the Earth and the distance to the Sun. So the distance to the Sun, around 93 million miles. So let's go ahead and plug in those figures and see what we get. So our side A is 4,000 still. side B is 93, 2, 3, 4, 5, 6, 93 million. So let's work out angle A. So angle A is 0.0025 degrees to two significant figures. So if A is 0.0025 degrees, then 2 times A, this angle here, is 0.005 degrees. Basically 0. Very, very close to 0. So we can see that because the sun is so far away, that rather than this angle being so steep between the observer on this side and the observer on this side, it's actually more like that. These two lines are basically parallel. They'll meet eventually, but not for another 93 million miles. It's been 93 million miles before these two lines meet. And so, to all intents and purposes, they're parallel. So the whole argument of having to pan to the right or pan to the left as the Earth rotates is ridiculous, because the sun's rays hit the Earth parallel. That's what we mean when we say the sun rays hit the Earth parallel. It doesn't mean they shoot out of the sun in a parallel manner. They shoot out in all directions. But when it hits the Earth, because it's so far away, the light that hits the Earth hits it parallel. So we can see that, and we can see the reason for that with this little graphic here. There's our Earth, there's our sun, a little bit closer to the scale as far as the size of the Earth and the sun is concerned. Nowhere near, but closer. And at this distance, that's the angle. If we move it further away, that angle reduces. Further away again, it gets smaller still. And further away, it gets even smaller, until eventually, 93 million miles away, it's practically 0. And these two lines would be parallel. Just about. Obviously, I can't show you that because of the scale involved. This Earth is about 3 centimeters wide on my screen. If this was actually to scale, then I'd need a screen about 350 meters wide to show you that. So, now we know that when the observer's on this side, he looks this way. When the observer's on this side, he looks this way. He's looking the same way all the time. So that immediately eliminates the zigzag argument. He wouldn't be zigzagging, he wouldn't be panning right and panning left. He's looking straight ahead, he's looking in one direction. Because the sun's rays are coming in parallel this way, no matter where you are, you're always looking in the same direction this way. So now I'm going to look at the rotation claim, that you're only rotating 180 degrees. Let's take a look. So here's our guy again. He's standing on this side of the Earth. Again, we're looking down on the Earth. And this represents magnetic north. Now, there's some, again, flat earthers that will say that if you use an azimuth app, which essentially locates your angular position in respect to magnetic north, that you would not rotate 360 degrees if you were on a spinning globe. That you would only rotate maybe 180 degrees, if that, because you're always facing the same direction. That's the argument that Rory had there with the guy looking at the beer. He's only looking in the same direction. His field of view is 180 degrees. There's a fatal flaw, though, that they failed to mention, and that's forgetting about your horizon. Now, when you're on the Earth and the Earth is rotating, you're seeing your horizon. This is going to represent the guy's horizon. And we're going to see that this will rotate 360 degrees around him as the Earth rotates, and that he will rotate 360 degrees in relation to magnetic north. So if he had an azimuth app on his phone, by the time he gets back to the start, in relation to this point here, he will have rotated 360 degrees. And while we're at it, we're going to look at one other claim that's made, is that because you would be going in this circle, that as you're going away from the sun, it would be slowing down, and as you're going towards the sun, it would be slowing down, and coming down this way and this way, it would be moving faster across the sky. So there'd be this speed difference in the sun. So let's have a look. Now we know the Earth rotates once per day, once every 24 hours. So what we're going to do is we're going to move our guy there in his horizon. Notice that he's looking at number 12 and he's looking at the sun. So we'll move him a quarter turn around the Earth. So he's now moved, and notice that when he started, magnetic north was to his back. Now it's to his left. So he's already moved 90 degrees in relation to magnetic north. In addition, he started looking at 12, and now he's looking at 9. Again, 90 degrees of his horizon has moved past him. Finally, if the Earth has travelled one quarter turn, then the time elapsed is 6 hours. And you've seen this clock face here. Each of these represents 2 hours of the day, because there's a 12-hour clock and there's 24 hours in a day. So he's effectively seen 6 hours of horizon movement, and the clock is showing 6 hours of horizon movement. So the sun has moved at a constant speed, one quarter turn round. Let's move him again. Now he's moved around again. He's rotated himself to stay looking at the same direction. Now he's looking at magnetic north effectively, and magnetic north is in front of him. He's now moved 180 degrees with respect to magnetic north. So his azimuth app would show him 180 degrees. In addition, he started at 12, then he saw 9, and now he's seen 8, 7, 6. And in the time that's elapsed, we know that's 6 hours from here to here. He's seen 2, 4, 6 hours worth of horizon. And if we model this in a constant speed, which I can't do with this software, but you would see that he would be moving in a constant speed relative to these numbers. So the sun would move at a constant speed around him, or appear to move at a constant speed around him. Finally, he moves up here. Again, he's rotating himself to keep looking at the sun. Now he's looking at 3. Magnetic north is over his right shoulder, so now he's moved 270 degrees with relation to this point here, to magnetic north. And again, 6 hours has passed. And then he's back to the start. And back at the start, he's back looking at 12. He's seen all the way around from 12 to 12 on his horizon. His horizon to him has rotated 360 degrees. Magnetic north to him has rotated 360 degrees. So his azimuth app would say 360 degrees. His horizon would tell him he's rotated 360 degrees. And the sun has remained in the same place. Now, the one difference between the globe model and the flat Earth model is, on a flat Earth, he would be rotating and the sun would be rotating around him. So as he rotates, he'd be seeing 360 degrees of his horizon, but he'd also be seeing 360 degrees of the sky around the Earth. On the globe model, or reality, the Earth rotates, he rotates in the opposite direction, and he only sees 180 degrees of the sky. But the sky's blue, and there's only one fixed reference point, and that's the sun. At night time, there's the stars, the planets, but again, they move in the same way as the sun does. They move across the sky in a similar fashion. So all those points outside of the Earth that aren't attached to the Earth are effectively fixed in relation to our guy there. So yes, you would only see 180 degrees of the sky. But when there's only the sun in the sky, it looks like it's moving around you. It looks like you're seeing 360 degrees of the sky. But you're not, and that's okay.